want you to imagine something very simple. A coffee cup, nothing fancy, just sitting there on the table. Now imagine I nudge it, it falls, it shatters. The pieces scatter everywhere. Now here's the interesting part. You've seen this happen 1,000 times in your life, but you've never, not once, seen the opposite. But I've seen shards of ceramic leap off the floor, reassemble themselves midair, and land gently back on the table as a perfectly intact cup. Now, why is that? Luck, a limitation of our imagination, or is there something deeper, some fundamental rule of the universe that quietly forbids this from ever happening? Today, I want to explore an idea that sounds like science fiction, but is actually rooted in very real physics. It is humble. A truck and coffee cup might hold the key to understanding why time travel, at least to the past, is impossible. Not because we can't build the machine, but because the universe itself won't allow it. Ladies and gentlemen, I want you to imagine something very simple. A coffee cup, fancy, just sitting there on a table. Maybe it's filled with coffee, maybe it's empty, maybe it's just been sitting there long enough that you stop noticing it, and that ordinary object, the kind of thing we overlook precisely because it behaves exactly the way we expect it to. Now imagine I reach out and give it a small push, a dramatic shove, just enough. It slides, teeters on the edge, and then gravity takes over. It falls, and when it hits the ground, it shatters, in all directions. Some large, some tiny, some spinning away faster than others. Maybe there's a sharp sound, maybe a few fragments bounce before settling. That's it. The cup is no longer a cup. It's a collection of broken pieces. Why? Now here's the curious part. Every single one of you recognizes this sequence instantly. There's nothing surprising about it. In fact, it would be strange if it didn't happen this way. But think carefully. Really carefully about what you've never seen. You've never seen those scattered fragments suddenly begin to move on their own. Be it a kapuša floor, hop over tiny obstacles, rotate into just the right orientation, and then almost magically snap back together into a perfect cup. And then somebody had but exactly right, down to every microscopic detail. No cracks, no missing bits, no sign that anything ever went wrong. And it's not just that you haven't seen it. You don't expect to see it. You don't walk into a room, notice a pile of broken ceramic, and think, well, if I wait long enough, this should fix itself. There's a deep certainty in your mind that this simply does not happen. What's really stopping it? Because if you think about it from the perspective of basic physics, the kind we learn early on, nothing obviously forbids it. The same forces are involved. Gravity, electromagnetic interactions, motion. The equations that describe how atoms move don't come with a built-in rule that says this direction only. Many of the fundamental laws of physics are perfectly happy running forward or backward in time. If you film the motion of particles and played it in reverse, the equations wouldn't complain. Mystery deepens. At the smallest scales, the rules don't seem to care about direction. But at the scale of coffee cups and people and everyday life, there is a very clear direction. Things fall apart, manage to come back together. So somewhere between the motion of individual atoms and the behavior of everyday objects, something changes. Perhaps nothing changes at all. And what we are seeing is not a new law, but the consequence of probability, of overwhelming likelihood. And thus, there are more ways for a cup to exist as a pile of broken pieces than as a perfectly ordered object. Statement can be in countless positions and orientations, but only one very special arrangement counts as a cup. So when the cup breaks, it's not doing something forbidden, it's doing something overwhelmingly likely and going the other way. And going the other way. What that would require every single piece, every atom, to coordinate in just the right way, at just the right time, with perfect precision. Not impossible in the strict mathematical sense, but so fantastically improbable that, for all practical purposes, it never happens. And that's where the real question begins to emerge. Physics allow both directions, but reality overwhelmingly chooses one. Let we go, the flow of time might not be written into the equations themselves, but into the statistics of how things tend to evolve. That's true, and reversing time wouldn't just mean running the equations backward. It would mean undoing this enormous tide of probability, forcing the universe to move from disorder back into order. Probability, forcing the universe to move from disorder back into order. The likely into the extraordinary unlikely. Now let's take that idea a little further, because this is where things start to get really interesting. The broken cup doesn't press upon it, it's up. We're not saying it violates any fundamental law for it to do so. There's no cosmic rule book that says thou shalt not unbreak a coffee cup. The motion of atoms, things like Newton's laws, or even the deeper quantum mechanical rules, don't actually forbid the reverse process. You could somehow track every atom in that shattered cup, calculate all their positions and velocities, and then reverse them perfectly. The system would, in principle, retrace its steps. The pieces would come together, the cup would lift off the ground, and it would land gently back on the table. So the real issue isn't possibility, it's practicality, because in order for that reverse process to happen naturally, without intervention, every single atom would need to move in exactly the right way at exactly the right way, at exactly the right time. Fractionally right, exactly right. A tiny deviation, even at the scale of a single atom, would ruin the whole reconstruction. The pieces would just bump into each other, scatter again, or settle into some other disordered arrangement. And here's the key point. The number of ways for things to be disordered is astronomically larger than the number of ways for them to be ordered. This idea is captured in a concept physicists called entropy, described as a measure of disorder, but that's a bit of a shortcut. A more precise way to think about it is as a count of how many microscopic arrangements correspond to the same overall appearance. A neat, intact coffee cup corresponds to a very small number of arrangements. A shattered cup corresponds to an enormous number. When the cup falls and breaks, it's not that the universe is trying to make it messy. It's simply moving from a less probable state to a more probable one. Rolling a pair of dice. You can roll snake eyes 2 once, but it's much less likely than rolling something like a 7. If you roll the dice over and over, you'll see the common outcomes more often than the rare ones. Now imagine something far more extreme than dice. Imagine trillions upon trillions of particles, all interacting, all moving. The ability between order and disorder becomes so vast that the ordered state is effectively never revisited. And this is what gives us the arrow of time. Fundamental law that says time must go forward, but a statistical tendency for systems to evolve from less probable configurations to more probable ones. But then we remember the past, not the future, because the past was more ordered. Cups break, not reassemble, because breaking corresponds to an increase in entropy, and reassembling would require an enormous decrease. Think about what time travel to the past would really mean in this context. It wouldn't just mean moving your body backward along some timeline. It would mean restoring the entire universe, or at least a significant part of it, to a previous, more ordered state. Every molecule, every photon, every tiny interaction would have to be reversed with incredible precision. It's not just the coffee cup that has to unbreak. Sound waves would have to unpropagate back into silence. The heat generated by the impact would have to flow back into the cup. The tiny disturbances in the surrounding environment, the air currents, the vibrations in the floor would all need to be rewound perfectly. But that's yet the degree-able, the more overwhelming it becomes, because all of these processes are constantly increasing entropy, constantly moving toward more probable states. To reverse time, you wouldn't just be going against one process, you'd be going against all of them. simultaneously, everywhere. It's like trying to take a drop of ink that has spread through a glass of water and forcing it, molecule by molecule, back into a single compact drop. That we live, not just in one glass, but everywhere, all but coordination. Now, here's where the idea becomes even more subtle, because you might be thinking, all right, maybe things don't naturally reverse. Maybe entropy tends to increase. But what if we're clever enough? We build a machine, something extraordinary at once, that can control every particle, every interaction, and deliberately reverse the process. After all, we already do small versions of this. Let me do. We can rewind a video. We can reconstruct broken objects, at least partially. We can even design experiments where systems behave in ways that look like time is running backward on a tiny scale. Though it's tempting to think that with enough technology, enough precision, we could scale this up. Not just fix a cup, but reverse an event. Not just reverse an event, but step backward in time itself. But this is where the problem shifts from being merely difficult to being fundamentally self-defeating. Because to reverse something like a shattered cup, you would need information. Not just a little bit, but an exact, complete description of the state of every particle involved. The matter video pitch fragment the surrounding air molecules, the energy exchanged in the collision, the microscopic deformations in the material, everything. That information, you would know what reverse even means. And here's the catch. That information doesn't just sit there waiting to be collected. Disperses. When the cup shatters, information about its original state spreads out into the environment. It becomes sound waves traveling through the air. Some of it turns into heat distributed among countless molecules. It is carried away in tiny vibrations you could never hope to track. The original neat description of a cup dissolves into an unimaginably complex pattern spread across. To gather it all back would require not only measuring every single detail, but doing so without disturbing anything else. A task that runs straight into the limits imposed by quantum mechanics. At scale, the very act of measuring changes the system. You can't perfectly know everything and leave it untouched at the same time. Before you attempt to reverse time, you've already lost the information you would need to do it. But let's suppose, just for the sake of argument, that you somehow overcome that. You build a machine so powerful, so precise, that it can track and control everything. Now another problem occurs, one that's even more fundamental. The machine itself is part of the universe. If it operates, if it processes information, if it makes decisions, it must obey the same physical laws. It generates heat. It increases entropy. That is good. To the very forward flow of time you're trying to reverse. Now you're asking a system that is itself moving forward in time, increasing entropy, to create a situation where entropy decreases everywhere else. Like trying to build a device that cools a room while it's constantly dumping more heat into it than it removes. The more powerful the machine, the more it fights against its own goal. And it gets even stranger when you think about the implications for cause and effect. If you truly reverse time, you wouldn't just see the cup reassemble, you would erase the memory of it breaking. Right? Or you wouldn't remember deciding to reverse it because that decision lies in what we call the future relative to the reverse process. So who exactly is operating the machine? By ear. In a fully reversed sequence, the operator's actions would also run backward. The invention to reverse time would itself be undone. The very cause of the reversal would disappear as the effect takes place. So the idea of choosing the time begins to unravel. A point outside the flow of time, a place where you can stand, make a decision, and then apply it to the universe without being affected by the same rules. But there is no such place. We are inside the system. Every thought, every action, every measurement we make is part of the same physical process. We don't get to step outside of it to rearrange it at will. Then the dream of reversing time starts to look less like a technological challenge and more like a contradiction in terms now. At this point, you might try one last escape route. Fine. Maybe we can reverse everything. Maybe we don't need to. Maybe time travel doesn't require rewinding the entire universe. Maybe we just need a shortcut. Ideas from modern physics start to sound almost like science fiction. Like wormholes, curved space-time, and the strange geometry described by Einstein's theory of relativity suggest that time is not as simple as a straight line ticking forward. Equations under very particular conditions. It's possible to construct paths that look back on themselves, what physicists call closed kind curves. And that sounds promising because now you're forcing every atom in the universe to reverse direction. You're imagining a kind of detour, a path that takes you from one moment to an earlier one without undoing everything in between. If you are the broken coffee cup refuses to cooperate because the problem hasn't really gone away, it's just been hidden. As you step into such a shortcut and emerge in the past, you find yourself standing in a room, and there's the coffee cup again, sitting peacefully on the table, just as it was before it fell. Radium looks normal. Nothing appears to have been reversed. The world seems intact. But now ask a simp what happens next. If the laws of physics still apply, and they must, then the same tendencies are still there. Battery still increases. Systems still evolve from less probable states to more probable ones. So from the moment you arrive, the future unfolds forward again. And here's where the tension appears. The presence in that past is an extraordinary likely arrangement of matter. The atom in your body is now in a configuration that, from the perspective of that earlier time, shouldn't exist yet. You are, in a sense, a pocket of the future inserted into the past. Like it's like that dog just sit quietly. They interact, they disturb, they introduce new pathways, new probabilities, new ways for things to evolve. Ripples, air molecules move differently. Heat flows, because the system is so sensitive, those differences don't stay small. So the idea that you could arrive in the past and simply observe it without consequence begins to break down. This is not neutral, it's a disruption. Now connect this back to the coffee cup. In the original sequence, the cup falls and shatters, a evaporated reaction. But if you're now in the past interacting with that system, you're altering the conditions under which that event occurs. But in a slightly different place. Maybe you stand in a slightly different place, shifts. Maybe your movement changes the timing by a fraction of a second. And once you do that, you're no longer dealing with the same event. So which version is the real one? The one where the cup breaks, the one where it doesn't, the one where it breaks differently. To make time travel consistent, you would need all of these possibilities to somehow reconcile. The universe traveler would have to enforce a kind of self-consistency, ensuring that no matter what you do, the outcome aligns with the history you came from. But that requirement is incredibly restrictive. Которые двигаются aren't truly free. It means every motion, every decision is constrained to avoid contradiction. You're not exploring the past. You're following a script that cannot be altered. And if you push against that, if you try to create a genuine change, you run straight into the same statistical hole we've been discussing all along. fail with shortcuts, even with the most exotic structures allowed by our theories. The fundamental issue remains. The direction of time is not just a feature of how we move through space-time. It's embedded in how physical systems behave, how probabilities are distributed, how order gives way to disorder.